Hello, here we consider a extension of many of the two sample or two population inferential techniques we saw in an earlier module. In particular here, well actually let me motivate it with an example. And so let's scroll down here to, I believe this is page 4. But on page 4, here's an example. Take a moment, read the problem setup, look at the data and the analysis. Okay, so here we are actually wanting to compare several population means. If you look at it, we're wanting to see, is there a difference in the average selling price of a home as a function of location? And so we had 6 data points per location, and here's well, let's see, let me focus on this. This is the sample means and the respective sample standard deviations of those 4 data sets there, and then here's the box plots for the 4 data sets there. And when you look at them, it suggests that there's a difference in the population means, but we want to test that formally, and that's what this module is about. So we want to test several population means, and let me just kind of give you a motivation here. Suppose we wanted to test 3 population means, mu1, mu2, and mu3. If that's the case, one way we could do that is run a test. So I'd have an H0 where mu1 is equal to mu2. I could also have another null hypothesis, another test where the null is that mu1 is equal to mu3, and then I can have a third test where mu2 is equal to mu3. And so what I have here are 3 hypothesis tests, presumably 3 t-tests that would need to be run in order to check to see if this hypothesis is true, or what the data suggests about the equality of all 3 means. Okay, so it turns out you can do that. You can run all possible pairwise comparisons, but an important disadvantage of doing that is that the probability of falsely rejecting at least one of the multiple t-tests, at least one of the hypotheses increases as the number of t-tests increases. And so what that would tell us is that if, suppose this test we did at the alpha 0.05 level, this one was 0.05, this was 0.05 as well, while the test individually would have a type 1 error rate or a significance level of 0.05, the overall type 1 error, that is, at least one of the tests incorrectly rejects a true null hypothesis, that overall type 1 error rate can be considerably larger than 0.05. And that's, you can look at your book for some examples of that, but we want to be aware of that. And so that's a major disadvantage. The overall type error rate, ultimately to do this hypothesis when you do multiple t-tests, can be considerably higher than 0.05. And so we need a way to control our type 1 error rate. In particular here, we need a single test of hypothesis that tests that all population means are equal. And we need it to be less tedious than the individual t-test, and we can also perform the test at a specified type 1 error probability. The test that does that for us is called an analysis of variance test, AOV. is abbreviated in our book, and this procedure looks at differences in sample means, and they are deemed statistically significant or not by comparing them to variation within samples. Now, one-way analysis of variance compares the means of a variable for populations that result from a classification by one other variable called a factor or a treatment. And the possible values of the factor are referred to as the levels of the factor. So in the location example that we started with in this module, there the factor or the treatment is location, and it had 4 different levels. Okay, bayside, bayfront, oceanside, oceanfront. Okay, so in order to test the equality of several population means, these are the assumptions that we need: that the populations are normally distributed, that the K population variances are equal, okay, and that the samples are independent of each other, and that they are selected randomly from each of the K populations. All right, and so if you look at just this, this assumption here is a extension, a generalization of the pooled t-test that we saw in an earlier module. All right. The hypotheses here that we could test, or the null hypothesis in particular, is: does mu1 equal mu2 equal mu3 all the way up to mu k? Are all the population means equal? Well, the alternative then, is the complement of that, would be that not all are equal, that not all the population means are equal, or that, you could say it this way, that at least one of the K population means differs from the others. Now this has a particular experimental setting, and it's got a special name for us. And when we take a random sample of observations of K different populations, this is called a completely randomized design. And we have in this table below, on the next page, a completely randomized design where there's 4 observations taken from 5 populations. And we're going to let Yij, so here Y now has 2 subscripts. But the first subscript tells us what population our observation came from. The second subscript tells us the observation number within that sample from that particular population. Okay, so here is some data here in a table. Now what we have are, say, 5 populations, and this is our data. Notice, so we got Y11 here. The first subscript tells us we are in population 1. The second subscript tells us we're in column 1. Really, that it's the first observation within the sample, the first sample here. Okay. Now, say Y23, just thinking about that, that is an observation that's from the second sample, or the sample from the second population, and it's the third observation within that sample. So it's designated as Y23. Now we can, for each of these rows of data, for these individual samples, we can compute a mean. And so it would be a sample mean. And so Y1 dot bar, that's the notation we use here. Notice the second, let me define it for you. It's the sum of Y1j, where j would go from 1 to 4, and then of course we would divide by, in this case, 4. So it's really just y11 plus y12 plus y13 plus y14. Okay. Um, so there's a sample mean for the first sample. Notice the second subscript with this y1 is a dot, and that dot is a reference that we basically summed over j, and that's what we've done. That's what we've done here. Okay. So, excuse me. A little more notation. Some of this is implicit, but Yij again is the jth sample observation from population I. Ni is the number of sample observations from population I. And so for the above, we see that Ni or N1 is N2 they're all the same. They're all equal to 4 rather. There's 4 observations in each of those samples. Okay, NT is the total sample size, and so for above, the total sample size would be 20. Okay, and yi dot bar is the average of the NI sample observations. So, and we reflected that in particular for the first sample here, but we could have that for the third sample, the fourth sample, the fifth sample, and in general the ith sample given by this expression here. And so for example, y4 dot bar is the sample mean again of those 4 values there. Okay. Y dot dot bar is the overall average, sometimes called the grand average, and we've got something here that's maybe a little strange to you. This is actually a double sum of the observations over NT. The double sum basically represents that we're going to add this to this to this to this. That represents the first inner sum. Then add that to the sum of these 4, then add it to the sum of these 4. And without getting into a lot of mathematical jargon, the double sum just basically means you add up all the observations into, or from this data set, you divide by the total sample size, and that of course gives you the overall sample mean. Okay? Now, what we want to do ultimately is we want to be able to represent variability in our data and ask the question, how much variability in the data is attributable to the factor or the treatment at hand? And so in the location example, there's clearly going to be differences or variability in selling price, but is there differences in selling price as a function of the location? How much of a factor is location in explaining the changes, or they're explaining the variability in selling price? And so what we do here is, and this is common within an analysis of variance, is you attempt to summarize the variability and then assign it according to different sources that are contributing to the variability. All right, so first we're going to look at here the total variability of all the samples, of the entire sample. The total variability, if you think back to just the single sample case here, remember we measured the variability by taking this is in terms of x, but that's okay. We took the sum of the square deviations over n minus 1, and that gave us the sample variance. We're doing a similar thing here, except our sum is a double sum because we've got to sum across each row in addition to the columns already. And so we have a double sum, and basically all this represents in here is a square deviation of the observation with its with the overall sample mean. And so this is just another measure of variability, we don't divide it by anything. We could if we wanted to, but we're not going to. And I want you to note that, well, let me come back to this expression here on the left-hand side. In the single sample case, we could have written this equation as n minus 1 times s squared, right? Just using a little algebra. Multiply both sides by n minus 1. And if you do that, then n minus 1 times s squared equals the sum of the square deviations in x. Okay, so that's an important principle, that if you want the sum of the square deviations, another way to get to it is to take the sample variance and multiply it times the sample size minus 1, and that's what this does right here. Okay, so we have this TSS, total sums of squares. This is a measure of the total variability in the data. Now, it turns out mathematically the total sums of squares can be partitioned into two pieces. What do I mean by partition? That it's separate, that these two pieces added together will give us back TSS. And so we've got this quantity here plus this quantity, add them together, that gives us TSS. And these two quantities by themselves are important, and we're going to look at those on this next page. That first quantity there is called SSW, or the within sample sums of squares. And this measures variation within the samples, as opposed to, say, variation overall, but it's sometimes it's called SSE in other settings, error sums of squares. But it just basically looks at, if we're within a given sample, what's the disparity measure. And so it turns out that mathematically this quantity can be written as n1 minus 1 times the sample variance for the first sample plus n2 minus 1 times the sample variance for the second sample, all the way up to nk minus 1 times the sample variance for the last sample. Okay? So this is an important quantity. It describes the variability within an individual sample. Now, another source of variability here is variation among, or sometimes called between, the sample means. And we can measure that by looking at this, what's called SSB, the between samples sum of squares. And what it does, it looks at a respective sample mean and compares it to the population mean, squares the difference, and then weights it by the sample size, and adds that up through every sample. And what that measures for us is how different are the respective sample means from the overall grand mean. Okay. Now, what we do with these sums of squares is now we compute what's called mean squares. And a mean square is defined as the sum of squares divided by its degrees of freedom. The degrees of freedom for SSB turns out to be k minus 1, the number of samples minus 1. The book uses this notation SB squared for that, so be aware of that. And the mean square within samples, MSW, denoted by SW squared in the book as well, is computed as SSW over the total sample size minus the number of samples or number of populations you're comparing there. Okay. And then finally we have a test statistic. So this test statistic is in place ultimately to make a decision about this hypothesis. Okay. And so we have this F test statistic here. This F test statistic is the ratio of MSB to MSW. All right, so if you want to rewrite it in terms of the sums of squares, you can write it that way if you want to. But it's the ratio of these two mean squares. It turns out this thing follows an F distribution with numerator degrees of freedom k minus 1 and denominator degrees of freedom nt minus k. Now when the null hypothesis is true, both of these mean squares, they estimate the same thing. Okay, and so it seems reasonable, and we would expect our observed F statistic to be close to 1 if each piece of this ratio is estimating the same thing. Okay, again, that's under the assumption the null is true. On the other hand, when the null hypothesis is not true, the MSB actually estimates something else, and so we would expect to see a larger numerator than the denominator, or a large F value. And in particular, large values of F indicate that the variation among the sample means is large, or larger, however you want to phrase it, is large, quote unquote, relative to variation within the samples. And if we get that sort of thing, that's evidence against the null hypothesis and for the alternative hypothesis. Okay, so we're going to reject our null hypothesis on 2 pages ago if our F statistic is large. Okay, we summarize all this stuff, this analysis of variance stuff, in a table. All right. This is called an ANOVA table. It's a common output within what JMP would give you. Even Excel with special kinds of packages can give you this kind of analysis of variance table, but it's a common representation of this sort of study. And what it does is it represents, basically, it represents the total variability, and also where the variability comes from. Let me back up. If I could adjust this video, I would. It basically tells us, okay, there's variability in the data, there's variability in the response, and some of that variability is attributed to the treatment or the factor, and this is a measure of that. And some of the variability is attributed to error, or in other words, is unexplained by the factor or the treatment, and this is a measure of that unexplained variability. And so we take the ratio of the associated mean squares, because it has a nice distribution, and we can talk about that ratio being large, and in turn can make a decision about the null hypothesis. Okay, so moving on to this example now.